Welcome to a presentation on the CVPR 2025 highlight paper on STING-B towards Vision Language Model for Real-World X-ray Baggage Security Inspection. Firstly, I will explain the motivation and background of our work. X-ray baggage monitoring plays an indispensable role in security operations. However, current methods are heavily dependent on manual screening and is prone to errors. Though researchers have attempted to make progress, there exist several challenges in the domain, including occlusion, heavy clutter, high intra-class variation, domain shifts across scanners, and so on. And thus, existing vision-centric models fail to generalize to different concealed threats and novel concealment techniques. A promising solution to these challenges is in leveraging the capabilities of vision language models in order to generalize across diverse threat items. However, there are several limitations. Existing X-ray datasets are unimodal and they lack textual descriptions. Further, the large multimodal models like GPT-4 or Gemini, they produce inaccurate descriptions or hallucinations when applied to X-ray imagery, as is shown in the image below. Here, this is an example of an X-ray image containing a 3D printed gun here. But when this imagery is given to the GPT-4, it claims that there is nothing dangerous in this image. And so does Gemini 1.5 and Lava Next also gives incorrect captions. Furthermore, the existing datasets also do not include real-world threats like the IEDs, 3D guns, etc. Now, to address these limitations, we introduce Strategic Threat Concealment X-ray or the STC-ray, which is the first multimodal dataset in this domain with over 46K image caption pairs spanning 21 categories. We also introduce the STING protocol, which is a structured threat concealment strategy that enables the generation of detailed domain-aware captions. We also propose STING-B, the first domain-aware visual AI assistant for X-ray baggage screening, providing a unified platform for scene comprehension, threat localization, visual grounding, and VQA. Now, further moving into each of these contributions, first is STC-Ray dataset, which is a realistic multimodal X-ray dataset that emphasizes on real-world threats such as IEDs and 3D printed firearms, alongside realistic concealment scenarios. And the different threat categories are shown here in this image. The STC-Ray data generation follows a systematic STING protocol that methodically adjusts the threat location, the baggage, the orientation of the threats, and the concealment levels. And later, the STING protocol generates the captions using these predetermined metadata to yield accurate descriptions. And this is vividly shown in the schematic diagram below. Our STING-B model is a domain-aware visual AI assistant which is built upon the Lava architecture. However, unlike Lava, which is limited to visual chat capabilities, STING-B uses specialized tokens to distinguish between the diverse VL tasks and deliver responses with tailored granularity. It uses specific task identification tokens for referring threat localization and visual grounding. STING-B, as is shown in this image below, is trained in multi-stage to build both domain expertise and grounding to leverage the LoRa fine-tuning approach of the LLM to preserve its general language understanding. So basically, in our training, we have two stages. The first stage is a multitask instruction tuning stage, which utilizes over 120K instructions to attain a generic understanding about the X-ray data. While the second stage is a threat visual grounding, which uses the grounding instructions specific to the multi-thread images in STC-Ray and 25,000 CT augmented images to enhance the STING-B fine-grained spatial understanding. Moving on to the experimental results, specifically in cross-domain scene comprehension where STING-B was evaluated over 62K images from three other datasets, the 6-ray, PID-ray, and the Combus XP, STING-B outperforms other VLMs in both F1 score and MAP. While for visual question answering, we developed an extensive benchmark with over 39K questions spanning 7 distinct question categories: the instance identity, instance counting, location, instance attribution, interaction, and complex reasoning. StingB achieves the highest overall accuracy of around 52.8%, surpassing both Florence, MiniGPT, and Llama. While in visual grounding and threat localization, we compiled an extensive test set with 57 questions from X6-ray and PID-ray, and SteamB achieves the best accuracy, beating both MiniGPT and Florence. We also compare StingB with other vision-centric X-ray domain-specific models in a cross-domain setting, and StingB outperforms both SDNet and PSN, which are X-ray specific models. Now for a short demo of the StingB model, we can see here the different questions which are being asked based on the image which is shown here, and these are the results which we get, the results from the StingB. So here it is being asked like what type of gun is it, and is it metallic or is it a 3D printer gun? So it answers it's a metallic gun, and then is a complex reasoning stage where you ask how it understands it and says bluish or greenish in color, it localizes the gun, and so on. Next is this is showing a 3D printer gun, and this is a power bank which it localizes a handcuffs, and so on. Moving on to the conclusion, we introduced STC-Ray, a multi-modal vision language X-ray dataset capturing real-world threat concealments. We also developed StingB, the first domain-aware visual AI assistant in X-ray security. Let us make X-ray threat detection smarter and safer. Thank you.